All right, let's talk about the chemistry that's hiding in plain sight. From the food you eat to the soap you use, it's pretty much all governed by this simple but really powerful duel: acids versus bases.
I mean, we've all been there, right? That awful burning feeling of indigestion or that curry stain that does that weird color change thing when you try to wash it out. Well, these aren't just annoying little problems. They're actually chemical mysteries. And the clues to solving them are all around us. So here's how we're going to crack this. We'll start with these everyday mysteries. Then we'll identify the main culprits. After that, we'll see how they react, uncover the secret role that water plays, and finally, we'll get a handle on the power of pH. Let's dive in. Okay, let's start with those mysteries in your kitchen and laundry room. The solution to both that indigestion and that weird stain actually comes down to the same fundamental chemical principle.
So think about that indigestion. Your stomach is just churning with too much acid. What's the fix? Do you fight fire with fire and drink something acidic, like lemon juice? Or maybe you try something like baking soda. Well, the answer comes down to one absolutely crucial reaction. And that reaction is neutralization. It's this simple, powerful idea that acids and bases basically just cancel each other out. They are chemical opposites. So to fight too much acid in your stomach, you need a base. And baking soda? That's a base. So to really get a handle on neutralization, we need to know who we're dealing with. It's time to get to know our main suspects: acids and bases.
A lot of the time, we can identify them with our senses. Though please do not go tasting things in a lab. Acids usually taste sour, like a lemon. Bases, on the other hand, are often bitter and feel kind of slippery, like soap. The most reliable test, though, is good old litmus paper. Acids turn it red, and bases turn it blue. Simple as that. But since we can, and really shouldn't, go around tasting or touching every chemical, we use these special substances called indicators. You can think of them like tiny chemical detectives that change color to signal whether you're looking at an acid or a base. And the crazy thing is, these clues are everywhere. You've got natural indicators right there in your kitchen, like turmeric, which, by the way, is exactly why that curry stain changes color when you use soap on it. Labs use synthetic ones, and some, called olfactory indicators, even change their smell. How cool is that? Okay, so we know how to identify them, but what happens when acids and bases actually react with other things? Now, this is where it starts to get really interesting. Okay, picture this classic experiment. You take some zinc metal and you drop it into some acid. Right away, you see bubbles forming. So if you collect those bubbles and bring a flame near them, well, something very specific happens. Pop. Yep, that unmistakable little pop sound. That is the definitive test for hydrogen gas. It's the signature result you get when many acids react with metals. The rule of thumb here is actually pretty simple. When an acid reacts with a metal, you get two things: hydrogen gas and a compound we call a salt.
And now for the main event, the ultimate showdown that explains our antacid remedy. When a base and an acid react, they neutralize each other completely. And what are you left with? Just salt and water. The acid is gone, the base is gone, and hopefully your indigestion is too. And what's really cool is that this acid-base pattern shows up in some really surprising places. It turns out that metallic oxides, like rust, actually behave like bases. And on the flip side, non-metallic oxides, like the carbon dioxide we all breathe out, are acidic. It's this fundamental pattern that runs through all of chemistry. So we've seen what acids and bases do, but we haven't really talked about why. What is the fundamental property that actually makes an acid an acid? Well, the answer lies in something we usually take for granted: water. So in this experiment, we've got a circuit with a light bulb, and the wires are dipped into a solution. If it's just pure water, nothing happens. But the moment you add an acid, the bulb lights up. This means the solution is now conducting electricity, and that can only happen if there are charged particles, we call them ions, moving around in there. And that, right there, is the secret ingredient. When you put them in water, all acids release hydrogen ions, that's H+, and all bases release hydroxide ions, OH-. It's these specific ions that give acids and bases all their characteristic powers. No water means no ions, and that means no acidic or basic properties. And hey, Because water is so crucial here, I've got to give you a super important safety rule. When you're diluting an acid, you always add the acid slowly to the water. Never, ever add water to the acid. The reaction releases a ton of heat, and if you do it the wrong way, it can boil and splash right back at you. So we know what acids and bases are, but are they all the same? I mean, is the acid in a lemon just as strong as the acid in your stomach? To answer that, we need a way to measure them, and for that, we need the pH scale. The pH scale gives us a number, usually from 0 to 14. A pH of 7, that's right in the middle, perfectly neutral. Think pure water. Anything below 7 is acidic, and the lower the number, the stronger the acid. And anything above 7 is basic, or alkaline, with 14 being the strongest of all. And pH can get, well, truly extreme. For instance, the source material points out that the clouds on the planet Venus, they're not made of water. Nope, they're made of thick, yellowish clouds of concentrated sulfuric acid. I mean, talk about a hostile environment. Which really brings us to a final, much bigger question. Here on Earth, all life, from the tiniest microbes all the way up to us, depends on this really delicate pH balance. So as we search for life on other worlds, maybe one of the most important questions we should be asking isn't just, is there water, but also, what's the pH?